Get started.
And you will find
Leave this cold place. Go back to warm Terra. See you, Michael. I'll begin with a word of prayer. Dear Father, we thank you for your grace and mercy to us each and every day. We thank you that you offer salvation so freely. If we'll just accept it, we thank you that we can be clothed in your righteousness, because our righteousness is like filthy rags. And again, Lord, we thank you for your many blessings to us this day. I just pray be with us. Help us to just understand a little slice of variational calculus today. I pray that the students will understand what we do. In your prayer, Lord Jesus. Amen. Okay, let me show you. Well, I'll start with a story. I was in the junior level physics course, and I was taking it with my friend Paul, who I affectionately refer to as Crazy Paul. And we were getting ready. I think it was for the second, maybe it was a second test. I think it was a second test in first semester classical mechanics. And I went to the professor and I said, well, I don't have to study that. And he's like, what do you mean? I was like, well, you don't test on theorems. And I knew those were fighting words. I knew what the effect that has on a professor to say such a thing. It was deliberate. I thought if I just said that, it would be on the test. It was not on the test. But about 3 months later, final. That question, that proof. The rest of the class was like, what was that? What was that question? And I was like, that was my question. It's the one question Crazy Paul got right on his final. It's the reason he passed mechanics. Let me show you what we learned. Is this. So, the derivation of the Euler Lagrange equations. Now I'm going to show you in a, basically you start with a, Hamilton's principle says that nature is lazy. Let's say you have an action, it's a function of j, it's a function of y dot, and say time. And so that's the integral over, no one cares about what the domain, well fine, time 1 to time 2, for some duration, and you've got some, well, I'll use L for Lagrangian of y dot, and possibly time. So this is Hamilton's principle of least action. It says that the equations of nature should be given by some sort of least action principle, that you can find some functional that if you minimize the solutions to that, they're the equations of motion for physics. And so how do you find critical points of a functional? Well, you take variational derivatives. All right. So what you do is you take the so-called delta of j. So to take the variation, and then so the way it works is you can pull the variation inside the integral. If you don't mind, I'm just going to write integral and stop writing t1 to t2 because it doesn't really have much to do anything. I'll put that back when I get time to be. The variation of L dt. Okay, so what's the variation of L look like? Well, L has 3 functions, right? Y dot, and t. So what you got is you got partial L, partial y, delta y, plus partial L, partial y dot, delta y dot, plus partial L, partial t, delta t, dt. But we consider a variation which is independent of time. All right, we fix endpoints basically, and so we're fixing n times. The variation doesn't. The delta t term I think that's gone. So that's 0 by assumption. And then, okay, so you got this integral partial L, partial y, delta y. And then, so here's the thing. You go, okay, well, the variation of ly dot, what should it be equal to? Well, that's not the right thing to say. The variation of, let's see here, I'm wanting to change this to, well, one of the things we can say is, well, variation of y dot, that's the same as, let's see here, delta ddt of y, so that's ddt of delta y, actually. Let's see here if I can figure this out. So ddt of partial L partial y dot. I'm sorry, guys. Yeah. So partial L partial y dot delta delta y, I think that's what I want. Yeah. So what's this? I got to do product rule, right? So I've got ddt of partial L partial y dot delta y plus partial L partial y dot ddt of delta y, right? But you see, this and this are the same thing, right? So basically I can rewrite this as plus ddt of partial L partial y dot delta y minus ddt of partial L partial y dot delta y dt. Fine, I'll put my bounds back in. And why does that matter? Well, when we integrate the total derivative, we just get partial L partial y dot delta y, evaluate from time 1 to time 2. And then what do we got? Integral from t1 to t2, partial L partial y, minus ddt of partial L partial y dot dt. Now we're considering a variation that fixes the endpoint. So we're assuming that delta y goes to 0 at the starting point and the ending point for the solution we're looking for. So this piece vanishes because these are separately 0 at the endpoints. And then I've lost my variation. There's a delta y out here, right? But this holds for arbitrary variations, and consequently we derive the Euler Lagrange equations, a necessary consequence for the equation of motions that they satisfy this little differential equation, which is known as the Euler Lagrange equation. Now what's the difference between what I showed you right here, right now, and what I showed you last class? What's totally missing? Remember last class I said y star is like the solution, and we built a family of functions around the solution which vary by a real parameter alpha. We differentiated with respect to that real parameter alpha, and from that we derived the Euler Lagrange equations, right? So there was no step in that derivation that was very kind of hokey, I would say. And I do use hokey in the derogatory sense. I know people think it's a positive term around here, but they're wrong. Sorry, but you know. Okay, anyway, whatever. So this, the pokey sense. Okay. Sorry, my standards for comedy are low today. So delta y dot, and see, there's just, I mean, why can you flip the variational derivative in ddt? Well, and I was always given an answer more or less along the lines of, well, that's the way it works. Which, to a person who's half a physics major and half a math major, is a very unsatisfying answer. It's part of what drove me to mathematics, is this. But there it is. here is how Crazy Paul passed classical mechanics right there, because he memorized this. I love it. Formal nonsense, but fun formal nonsense, right? Now, the reason this is called the Euler Lagrange equation is what it sounds like. It's due to Euler and Lagrange. These are separate people. If I understand the history right, the way Euler solved this, all right, was something like this. You've got, your typical fixed endpoint problem, and he imagined some solution like this with these like joining points for possible solutions. He put, if I understand correctly, Euler put coordinates on the joining points, right? And converted this problem to a problem in many, many variables, and solved basically the critical point problem from that, and somehow from that got to these equations. That's Euler. I have no idea how on earth he ever got from looking at variables on these points that make up the solution path to that equation. I have never looked into the history of it, but I think that's a deeply fascinating thing. It seems very complicated to me. Lagrange pretty much wrote it just as I wrote it here. So in physics, we study Lagrangian mechanics, and it's due to Lagrange. He wrote these. It's a way of doing classical mechanics that's quite divorced from what you've seen in the introductory class, supposing you've taken it. All right. And we'll get to that a little bit later today, but I want to show you one or two more just classical variational calculus problems that are interesting. So I'll start with, well, you guys, what do you want? How about, I'm not going to give you a choice. What am I saying? How about the surface revolution with minimal area? So let's look at the surface area problem. So here's y, here's x, and you take 2 points, say x1, y1, and over here x2, y2, and you can imagine rotating this curve. Imagine rotating the curve around the x-axis, right? What do you get? A disk? Well, no. Rotating around the x, so it looks something like, one of these deals, right? And so what's the surface area? Excuse me. Right, pretty much that. So you got to think about chopping this thing up into little ribbons, right? So yeah, what's the surface area? What's the dA for one of those ribbons? First of all, the radius of it is essentially y, right? So 2 pi y, that gives me the sort of the circumference of that ribbon. What's this? It wouldn't be dx. We got to account for the way it's sloping up. Yeah, you want the ds here. Now, yeah, the arc length. Now, ds in terms of we're being pretty boring here. We're saying that this is y is equal to f of x. We're not doing anything too snazzy, parametric here. Just a graph. So the arc length for a graph is the integral of the square root of 1 plus, f prime of x quantity squared dx. Yeah. So I gotta do 2y, or if I put y equals to, if I let f of x equals to y, then f prime of x is y prime, right? So I really have 2 pi y square root of 1 plus y prime quantity squared. I'm going to write that y dot squared, though, just for the sake of, I hate primes, and dx. Oh, fine, y prime. Sorry, I'll get over it. Then you have to integrate that from x1 to x2. That will give you the surface area, right? So look at that. So we have the integral from x1 to x2 of 2 pi y square root of 1 plus y prime quantity squared dx, right? If you will, that's the surface area. I can call this thing, I don't know, J. So that's essentially the thing we're trying to minimize. So you take the variation of this, and through the same thing we just went through over here, the solution has to be solved through Euler Lagrange equations. Okay, so what are the Euler Lagrange equations? So the Lagrangian here is L. And so what we got, we need to look at partial L, partial Y is equal to what? It's just, right. Notice that here we're treating y and y prime as if they're independent. You're like, but y prime is the derivative of y. They're not independent. What do you mean? Exactly what do you mean when you do such a thing? It means really you're changing your problem from the one that's given to a problem in higher dimensions where you can support this independence of y and y prime. If you want to get into the technical mathematics of that, you're working on something called a jet bundle, where you have independence of the variable and its derivative. It's a technique. Partial L, partial y prime is what? 2 pi y divided by 2 times the square root of 1 plus y prime squared, right? And then times the derivative of the inside function, which is going to give me a 2y prime. You guys with me? So my Euler Lagrange equations, I'll do them up here, is that partial L, partial y is equal to d dt of partial L, partial y prime. And what is that? That is going to give me 2 pi square root of 1 plus y prime quantity squared equal to, I guess, 2 pi y prime over square root of 1 plus y prime squared. Oh, sorry. What am I forgetting? Kind of important. The d dt, right? Some of you are in differential equations right now. Wait, one of you is in differential equations. How many people are in differential equations right now? One? That's it? Oh, okay. Yeah. All right. How many people have had differential equations before? Oh, I'm sorry. I was distracted by something in my notes. So 3 of you. So you guys remember how to solve that? It's a trick question. We don't teach you how to solve these in differential equations. And in fact, I have chosen, this is not a wise path. I mean, I can try a little bit more. This is what? Square root of 1 plus y prime quantity squared is equal to d dt of y prime over, I just canceled the squared. I mean, I canceled the 2 pi. I don't know if this really helps. I mean, this much I can do. Okay, great. Yay. That's the Euler Lagrange equation. Now there is a way you can rewrite this. You can rewrite this differential equation as follows. There's the variation, not in the technical sense. There is a way you can rewrite this equation, just chain rule differential equation stuff, as partial L, partial y minus d dt, big parentheses L minus y prime partial L partial y prime equals to 0. This is an alternative form of the Euler Lagrange equations. Let's see here if I can explain why that is. See, when I wrote these notes, it was a homework problem to show that. And I've already given you homework, so I can't make it your homework problem. Dang it. It's kind of annoying. It's what? Oh, kind of fantastic, yeah. There's some way to derive. So I think I'm saying that you can, sorry, this is for the y prime. Oh, I used dots, didn't I? But if you convert to, oh, and I've got x's over there, right? So like the corresponding thing over here for us would really be, there's an x here. Oh, no, sorry, that's a y. This would be x. And then it's fine. Okay, so let me just go ahead and write that one down. So partial L, partial L, partial y. Why is that helpful?
So why or why prime have any g's in it anywhere? Print or something?
I'm not happy.
What was there when you do d dt of those functions over there? Do you mean d dx?
Oh, yes. I'm sorry. X is my independent variable here. Good grief.
Because if it's g, it's a whole lot easier.
Yeah, that is definitely X.
There's no g dependence on anything.
Yeah. No, X. Those are definitely X's. I'm sorry. I'm. This is the danger of having one foot in one world and in another. Like the one world is classical mechanics, all right? The independent variable is time. The other world is classical problems of variational calculus. There, the independent variable might be X, it might be time, it might be 7. Yeah, it might be other stuff. So, okay, let me if you differentiate, oh man, I do not want to differentiate that. Golly. Oh, no. I do not want to differentiate that.
Do you feel like you're integrating the other side?
And I don't see how, the other thing is I don't see how my other alternative form helps either because, well, fine. Let me just write down what I have in the notes. I'm not seeing how I got it.
Can you integrate the left side? Or integrate both sides? You get the
Well, I somehow get from here, well, the trouble is, to do that, I'd need to know the answer. Well, at the moment, it's a dark magic to me, but I say that you can rewrite this as 2 pi y times the square root of 1 plus y prime squared. I've already violated my prime directive for today, which was not to get into these kinds of picayune details, which are not enlightening and are half wrong at the moment. Let's see here, so plus 1. I mean, they're not. What I'm doing is not wrong. It's just not complete, let's say, okay? And there's a rather large jump. I'm not sure I believe it. Oh.
Well, you shouldn't have taken out the 2 pi then.
Oh. This is not. Actually, this is fine. So, incorrect, guys. This is actually an x. That's what makes this a genuinely different equation. So partial L partial x minus t dx of that. It's the independent variable over here. So that's that. If you can derive this, and I'm pretty sure I won't be able to right at the moment. My mind is not clear on it. But it's chain rule. I promise it's just the chain rule in this context thought about correctly, that derivation. Once you have that though, so using Lorenzo, you need to zoom in on this right here. This star equation here. So for the problem we're looking at right now, this is 0 because there's no explicit x dependence in the Lagrangian. So the Euler Lagrange equations just become a total derivative of the Lagrangian itself minus y prime times partial L partial y prime. And that's what this is. So the Euler Lagrange equations, the normal ones that I derived, started this class and last class, they're kind of ugly, as we were just kind of starting to appreciate. You don't want to really solve these directly. It's much nicer to solve this. Differential equations doesn't really help you much here either. But what does help you? How do you solve this thing I'm about to underline in green? Algebra? Algebra will be required. I mean, I have the derivative of stuff is 0. What's that say about the stuff? It's constant. So that gives me, 2 pi y square root of 1 plus y prime squared minus 2 pi y prime squared over the square root of 1 plus y prime quantity squared equals to some constant k. And then you can make a common denominator, right? And just get rid of the 2 pi, put the 2 pi over into the constant, all right? And so what we have is then, y times 1 plus y prime quantity squared minus y prime quantity squared divided by the square root of 1 plus y prime quantity squared is equal to, k. Find k over 2 pi, which I will now call, I'm not going to call it 7. I'm going to call it big K there. And so what we have then is we have big K is equal to, you see the y prime, see these cancel? Which is nice. Parenthesis missing. So these cancel and you're just left with y over the square root of 1 plus y prime quantity squared. Now, square both sides. I've got big K squared equals to y squared. Oh, it's unfortunate. 1 plus y prime squared, which gives me k squared plus k y prime quantity squared equals to y squared. What is it?
Squared on the outside of that parenthesis. It's the y prime itself that's squared. On the bottom line. But it looks like it's a binomial. Above that in the numerator. Looks like the squared. Numerator of the bottom line. It's the y prime should be squared itself, not
Y,
outside.
yeah, y parentheses 1 plus parentheses y prime parentheses squared parentheses.
That probably should.
You got it.
I'm not seeing
The
it.
little k on the bottommost equation.
Okay, up.
Point to the little k on the bottommost equation. Now go left a little bit and put a parenthesis. Right there. Put a parenthesis on the end of that. Right?
No.
Keep on keep going. Further in, right before the minus.
Up. That's
Oh.
squared.
Oh, okay.
Yeah. All right.
I was like, how does that cancel out?
Yes. All right. So we get to this, which we can rewrite as y squared minus k squared equals to k y prime quantity squared. And so, okay, so what you do then is, let me rewrite this a little bit. This is really k times dy dx quantity squared, right? And so you can actually solve that then. You've got yourself a k dy over y squared minus k squared square root is equal to dx. And so integrate both sides. We get x is equal to the integral of, k dy over the square root of y squared minus k squared. Yeah. Which is what? I mean, that's just obviously inverse hyperbolic cosine of y over k, right? No? Calculus. Oh, fine. You make me derive my inverse hyperbolic cosine derivative?
No. I trust you. We just don't have it memorized. Trust you.
Well, I mean, I have notes. No, I mean, it is. I do think it's this. And then you can just solve both. I mean, there's a constant. And then plus a constant, right? So, anyway, some details, I guess, plus a constant. So this gives us something like cosh of x, right? Plus, I don't know, I'm being a little bit vague about the choice, the appearance of the constants here. I guess I'd have plus c here, right? So if I guess I'd rather put the c over here. I don't know, I mean, it's something like cosh of x plus c is equal to y over k. So you got something like k. Solution, finally, y is equal to k cosh of x plus c, something like that. And then you can choose the right value of k and c in order to fit the initial data points. All right. What is this called? What is such a surface known as? Indeed, this is a catenoid. Catenoids are the shapes which, for example, so bubbles take to minimize the surface area. So, variational calculus derives that for you. Well, variational calculus gives you an Euler Lagrange equation, or variational calculus paired with the proper chain rule to get the equation into a nicer form, paired with a little bit of just combination of pre-calculus, common sense, sometimes actual differential equations, standard material, and just persistence gets you to the catenoid. I mean, there's really, I'm telling you, Lagrangian mechanics is very general, right? So you should expect that the differential equations which appear from the Euler Lagrange problem, you should expect that the Euler Lagrange equations are rather unpleasant in general, because they're describing pretty much how to set up very arbitrary types of problems. And those different types of problems will have really radically different kind of, how to actually solve the equations. That's much harder than setting them up, right? So a fair question for the test would be something like derive the Euler Lagrange equations given this Lagrangian. That's almost an embarrassing question to ask, because that's simple. It's really simple. All you have to do is take the partial derivative of the Lagrangian with respect to the dependent variable and set it equal to the derivative of the Lagrangian with respect to the velocity of the dependent variable. Done for one variable, right? I want to show you another classic problem, and then I'll actually get back to the problem of classical mechanics. And I will show you, once we get past this next example, I'll show you how we can derive Newton's equations from the Euler Lagrange equations, among other things. Things go well here. I do have another class left over for this material, so we don't have to get through everything today, but I do want to keep it moving. And as fascinating as it might be to watch me solve one of these in gory detail, it's probably better if I go on. Well, I think I just did solve it in gory detail, didn't I? Modulo this little jump. So this is old, right? Variational calculus is very old. I said Euler. Euler's 18th century, right? You're like, is that the same Euler of like the Euler formula from complex? and Euler's theorem in number theory, and the Euler today in differential equations. The Cauchy-Euler problem. Yes, the same Euler. Dudes everywhere.
I didn't know we were doing that today.
I just know. I could sense it in the room.
Dr. Lane.
I saw the board. I saw the board. So oh, come on. You know, it's so annoying. You actually have to plug it in for it to work. So strange, but. Maybe.
Your computer.
Yeah.
It was perfect.
So it's my computer's dying. All right.
Do you have a VGA?
That's what I'm doing.
Do you have HDMI?
I don't know if I have an HDMI. What would that look like?
It kind of looks like a USB, but like wider.
Oh, is this? No.
That's the USB. There should be an HDMI.
What does that look like?
There is not an HDMI.
This is old. Okay.
Huh.
Oh yeah, because it's got no HDMI thing.
Yeah.
It's cool.
I wonder if this would work.
No, that's for other things, I think. It's okay. All right, so it's like it always has been.
Probably, yeah.
But you can this.
Your computer yesterday and complex analysis, and it did not go yellow in that room.
Huh? That's right. What's the? Huh? I don't know. Okay, so I drew you the picture here today, right? So the next problem I'd like to describe for you or talk you through here is known as the hard word, brachistochrone. The brachistochrone is let me set up the problem for you. This is also a very old problem. So here's the problem. You got a point here, say x, I guess we say x2, y2. And then you've got a point over here, let's say x1, y1. These points are given, all right? Did I set it up right? x1 from x1. Oh, I've already set it up wrong. And so I'm taking this to be 0, 0, right? So the question is, what's the curve of quickest descent? So here's the rules for the thing. You know, you've got some curve like that, and you imagine that there's some bead with mass m or whatever, and it's sliding along this without friction. The question is, which curve, if you constrain it to, does it slide in the quickest time under the influence of gravity? Now, if x1 is equal to 0, then we can answer the question without variational calculus. The answer is straight line, right? But if it's not, then this is actually a very difficult problem. Kepler, not Kepler, Galileo tried to solve this. And Galileo said that the answer was a parabola. He was wrong, not a parabola. But then again, Galileo also didn't have very good mathematics to work with. So we can't be too down on him. So the first thing to do is to set up an action principle which calculates the time it takes. So how do you calculate the time it takes for the curve? Basically, the energy is conserved since there's no friction, so you can use the kinetic energy to relate the speed to the everything else involved here. So 1/2 mv squared is equal to mg y minus y1. So what I have here is that the kinetic energy at the end is equal to the potential energy at the start, right? And but on the other hand, I can solve that for v. V is ds dt. So since v is ds dt, I can solve for dt, and dt will give me this 1 plus y prime squared over 2y times y minus 1, y1 minus y dx. Let's see where the dx come from. I'm trying to remember. Oh, the ds I traded for an integral over x, right? So I would have ds over this to get dt, but then the ds is the square root of 1 plus y prime squared dx. Same, just like the thing we just did, right? The ds becomes the square root of 1 plus the f prime of x, well, y prime, because we're thinking of y prime as being an independent variable from y. So there you go. There's the Lagrangian. And again, there's no explicit x dependence here. So the easiest way to solve the differential equation is to use the modified Euler Lagrange that's set up to be a total derivative. All right. Like I have this one, but for this problem. And so when I do that, I get this, which gives me, well, the partial derivatives, anyway. It's complicated. So after a little bit of algebra, you get to that, and then you get to this. And then you get dy dx squared. You take the square root. It gives you these lovely equations. Dy dx is plus or minus the square root of b plus y over a minus y. That then you can separate and integrate. You get integral of the square root of the quotient of a minus y over b plus y. That's not an easy integral to solve, but it turns out that cycloids are the solutions to those. So the cycloid, these are the solutions to those. X equals to this and y equals to that. What it is if you had if you have a wheel rolling along the floor, and if you put a point on the wheel and then you study the motion of that point as the wheel rolls, that gives you a cycloid. So if I could somehow make my finger go in a circle smoothly and then just kind of walk sideways and you followed my fingertip, that would be a cycloid, like that. If I could actually do a circle and walk at a straight, at a steady pace. And then the interesting thing, though, is once you have that solution, you can go back and say, okay, so what is actually the time of descent if you follow one of these cycloids, right? And it turns out when you do that integration, I can show you it's about a page. It's involved. The time, though, is pi over 2 square root of y1 over 2g. The interesting thing about this is it has no connection with x1, y1, except that they both reside on the same cycloid. So it follows that the period of a pendulum that follows the cycloidal path is independent of the starting point on the path. So if you had a cycloidal path like this, it wouldn't matter if I started here or if I started here. Anyway, it would be the same period. And then you can actually generate one of these curves by wrapping a string around a cycloid. So you can make like a pendulum that, as the swing decays in amplitude, the period stays the same. So it's kind of interesting. You're like, but the period.
Is that physically possible?
Yeah. Like I said, if you make the string follow a cycloid, it turns out that the involute is also a cycloid. So if you make this, I'm not doing it very well. So here, and then I'm wrapping there. This, I'm not doing a very good job of it. This point out here is the involute. If you wrap a string around another curve and then follow the endpoint of the string, it gives you something. Actually, I forget if it's an involute or evolute. Anyway, you can, through some quirk of curve geometry, set up a string to follow a cycloid by making it wrap around a cycloid. But so you can actually construct pendulums with constant periods using this geometry. It's kind of funny. All right. If you had a function of not just one variable, but if you had a Lagrangian that had more than one variables, like y1, y2, yn, and then, of course, also velocities, corresponding velocities, y1, y2, yn prime, or dot, if you like. Then when you do the variational principle, the chain rule has more terms in it, but pretty much you can go through the same derivation, and you end up with these Euler Lagrange equations: partial f partial yj minus ddt of partial f partial yj dot is equal to 0 for j equals 1 to n. These are the Euler Lagrange equations for n dependent variables with, again, just one independent variable, which I'm taking to be time. Anyway, this projector is being stupid to me, so I'm going to put it away. Anyway, I didn't want to write out. As you can see, it would have taken me, considerable effort to even go through part of the derivation of the Dirichlet-Christocohn problem, but I think it's interesting and you should see it. Yeah. You can also derive Snell's law by a least time principle. If you look at if you minimize the time by a light ray going through a medium, because the index of refraction is what? It's the speed of light. How's it go? N is c over the velocity inside. Another application. N is c over v, right? So this is the index of refraction. Index of refraction. C is a constant speed of light in vacuum, right? And then v, well, v is ds over dt. So you can actually, if you think about, 2 points, whatever, and suppose it says index of refraction n1, this is index of refraction n2, and you want to find a path between 2 points in the medium, which minimizes the time between the points. You can just set up basically, well, dt is what? dt is ds over v, right? But it's that. What is that in terms of n? What's v equal to? C over n, right? So I think you can do n over cd. Well, what? Oh, nds over c. Yeah. I'm not sure. I can't remember which I actually do the integration in, but anyway, I'll post the solution in course content. You can actually derive Snell's law from looking at the Euler Lagrange equations and minimizing time. I'm not sure what I want to pick as the actual integration variable. So, Anyway, let me transition now to a much more focused series of examples. I would find it and project it, but that seems like a fool's errand today. Let's talk about classical mechanics. So what's the problem of classical mechanics? The basic problem is this. Suppose you're given, bunch of particles or some continuous distribution of mass, right? And you want to understand what are the forces involved on the masses and what's the motion of the masses as a response to those forces, right? That's essentially the story. So Lagrangian mechanics takes a slightly different approach. Instead of forces being the central concept, energy is the central concept. So the starting point of Lagrangian mechanics, well, an efficient starting point for Lagrangian mechanics is you write down, you know, for a given system, and let's say, I don't know how many you know, 3 dimensions. So you might have with particle. Well, do I want to do n particles? I'm sorry. Let me just be vague. For a given system, you write the Lagrangian. And the Lagrangian, what you write it as, is it's equal to t minus u. The t is the kinetic energy, and the u is the potential energy for the system. So you write down the Lagrangian for the system by adding the kinetic and potential energies, and then you calculate the Euler Lagrange equations. Those are your equations of motion. That's pretty much it. There's also a method of Lagrange multipliers that you can use or not use if you want. Step 2. So step 1 is that. Step 2 is you know, write down the Euler Lagrange equations. And try to solve them, right? I mean, if you're a physicist, you want to solve them, you want to understand them, you want to tear them apart piece by piece and really understand. I mean, that's your central tool to analyze the physical nature of something. These are the Lagrange equations. So let's suppose that we have, well, let me show you some examples. I guess there's a couple of major questions here. The 2 major questions really are, how do you set up the kinetic energy, and how do you set up the potential energy, right? Those are kind of the 2 central starting questions. So let me start out with a relatively simple example as to connect with maybe what you already know. So example 1. Suppose we have mass m, and so I'll keep it really simple. One-dimensional problem. Mass m, 1 dimension, right? Subject to what? To force F, right? The force is minus du dx because that's the potential energy in 1 dimension, right? Minus du dx. And so the kinetic energy, which is T, is what? 1/2 mv squared. I'm not even telling you what the U is. I mean, different U's. For example, in your basic course, maybe you've seen U is equal to maybe mgy. Oh, x, I'm using x, so mgx, or 1/2 kx squared, etc. These are possible examples. Gravity, if we're thinking of x as the vertical direction, or the spring potential energy is another example. These are the usual examples. What's the Lagrangian in this case? Well, the Lagrangian, well, we have a single mass m, right? So what do you need to describe it in terms of what are the variables? You need x, you need x dot, and possibly you need time, right? So x dot, t. I wouldn't usually write that. I usually just call this thing L. And what is it? It's 1/2 m x dot squared. See, because v is x dot here. And then what? Minus, well, plus u. No, minus u, yeah. So the Lagrangian's not energy, all right? It's kinetic energy minus potential energy. And then what? So the Lagrange equations will be what? Partial L, partial x is equal to what? D dt of partial L, partial x dot. So what's partial L, partial x here? What's that? So it apparently it's minus partial u partial x, right? Since we don't know better. Right. U is some function of x, I should emphasize, generally speaking. Well, u is related to the force. Also, it's minus the derivative of the force. I mean, minus derivative of u is the force. Okay, so this is equal to what? D dt. What's partial L, partial x dot? Partial L, partial x dot is mx dot, yeah. So what's this become? This is the force is equal to mx double dot, assuming the mass is constant. And this, of course, is ma. Force is equal to ma. This is the simplest example I can think of. But it's an important example, right? How about 2 dimensions? What's 2 dimensions look like? One particle. Actually, let me go to 3D. 2 dimensions is too boring. We'll just skip straight to 3 dimensions. So again, we want L is equal to T minus U. But this time, the kinetic energy is 1/2 m in Cartesian coordinates, x dot squared plus y dot squared plus z dot squared. Because the speed squared, right, v squared is what? It's the velocity, the magnitude of the velocity squared, which is exactly this. It's x dot squared plus y dot squared plus z dot squared. And then minus u. But this time u is a function of x, y, and z in principle, right? So generically speaking, there's the Lagrangian for a particle in 3 dimensions. All right. And so what are the Euler Lagrange equations? Notice that partial L, partial x dot is equal to mx dot. Partial L, partial y dot is my dot. Partial L, partial z dot is equal to mz dot. It's no accident that this is the momentum in the x direction, this is the momentum in the y direction, this is the momentum in the z direction. Okay? Not an accident. And then what would partial L, partial x would be minus partial u partial x, right? Which would be the x component of the force. And this would be the y component of the force. The z component of the force. So we get 3 Euler Lagrange equations, one for each dependent variable, and they're the x, y, and z components of f equals to ma as a vector equation, right? So you either have f is equal to ma, that's interchangeable with these 3, Euler Lagrange equations, which I'll just write together as one. Partial x sub j dot equals d dt. Oh, partial x partial j is equal to d dt of partial L partial x j dot. So how would we find the kinetic energy in other coordinate systems? How would you write the kinetic energy naturally in terms of, say, suppose you have r of t and theta of t are the polar coordinates of some point going in the plane. How would you express the speed squared in terms of polar coordinates? How would you derive that?